بسم الله الرحمن الرحيم. توقفنا في المحاضرة السابقة حيث العوامل التي تؤثر في ability of hemoglobin to reversibly bend oxygen وكانت pressure of oxygen pH pressure of carbon dioxide and availability of 2,3 bis phosphoglycerate. Today we will begin in the first factor, which is heme-heme interaction. The sigmoidal oxygen dissociation curve reflects specific structure change that are initially at one heme group and transmitted to other heme group in the hemoglobin tetramer. The net effect is that the affinity of hemoglobin for the last oxygen bonded is approximately 300 times greater than the affinity for the first oxygen. As we said previously, the first binding of first molecule bend to the hemoglobin increased the affinity for the hemoglobin to bend for the second and the third and then the fourth oxygen. Loading and unloading of oxygen. In the lung, the concentration of oxygen is high and hemoglobin become saturated or loaded with oxygen. In contrast, in the tissue, we find it is exohemoglobin release or unloaded much of its oxygen for use in the oxidative metabolism of the tissue. The range of oxygen concentration that occur between the lungs and the tissue permit hemoglobin to carry and deliver oxygen efficiency from site of high to site of low oxygen. As we see in the dissociation curve, oxygen dissociation curve, we find out that the difference of pressure between the lung is very high and the tissue is very low. In the lung, the saturation of oxygen is very high. In the tissue, the concentration of oxygen will be very low. The large difference between these concentration let the hemoglobin delivery oxygen or release oxygen when it transported to the tissue. Myoglobin could not achieve the same degree of the oxygen release within this range of partial pressure of oxygen. Instead, it would have maximum affinity for oxygen throughout this oxygen pressure range and therefore would deliver no oxygen to the tissue. الفرق ما بين الهيموغلوبين والمايجلوبين. في حالة الهيموغلوبين يوجد فرق كبير ما بين تركيز الأكسجين في الرئة وتركيز الأكسجين في التشو في الأنسجة، وبالتالي هذا الفرق الكبير يؤدي إلى فقدان الهيموغلوبين اللي هي الجزيئات الأكسجين عند وصوله إلى التشو. أما في حالة المايجلوبين فنلاحظ أن الفرق يكون في الافينيتي فور أكسجين نسبيا قليل، لأنه at low pressure in the tissue the affinity of myoglobin for oxygen nearly is high. Bohr effect. The Bohr effect بشكل عام يوضح لي العلاقة ما بين تأثير ال pH وتأثير اللي هو concentration of carbon dioxide على الافينيتي of hemoglobin to oxygen، حيث يلاحظ أنه عند low pH بمعنى high acidity the affinity of oxygen is very low. Also at high concentration of CO2 the ability of oxygen, the affinity of oxygen ability of hemoglobin to binding with oxygen also is very low. Both result in decreased oxygen affinity of hemoglobin and therefore a shift to the right in the oxygen dissociation curve. This is the Bohr effect. And the Bohr effect هو decrease oxygen affinity of hemoglobin due to decrease pH and increase CO2 pressure. Raising the pH or lowering the concentration of CO2 results in the greater affinity for oxygen, and it will shift to the left in the oxygen dissociation curve and stabilization of the R or oxy form of the hemoglobin. As we'll see in this curve, we find by decreasing the pH, increasing the acidity, the curve will shift to the right here. At we find that at the same percent of saturation of oxygen, for example 50, we find that it need less pressure for high low pH, but it need high pressure for the low pH. So by decreasing the pH, the lowering of affinity of hemoglobin to binding oxygen. But what is the source of decreasing of pH? What is the source of H positive, which lowering the pH? According to the equation, we find that carbon dioxide react with water in equilibrium reaction to produce carbonic acid. Carbonic acid is spontaneously dissociate for bicarbonate ion and hydronium ion. Hydronium ion produced by this pair of reaction contribute to the lowering of the pH. So the lowering of the pH is contribute for the increasing of H positive in the reaction. This different pH gradient, that is lung having higher pH and tissue having lower pH, favor the unloading of oxygen in the peripheral tissue and the loading of oxygen in the lung. So at high pH, high affinity for oxygen, so it is loaded in the lung. Low pH, low affinity for oxygen, hemoglobin to oxygen, وبالتالي it is unloading of oxygen. Hemoglobin is more efficient transporter of oxygen. Mechanism of the Bohr effect. According to the equilibrium reaction here, we find out by increasing of hydronium ion or decreasing of oxygen pressure, the reaction will go forward. Then it is unloaded. But by decreasing of H positive, meaning decreasing of pH of H positive, meaning increasing of pH, or increasing of oxygen concentration, oxygen pressure, the reaction will be reversible. So oxygen binding hemoglobin concentration increase. Deoxyhemoglobin where an increase in proton or lower oxygen pressure shift the equilibrium to the right, favoring deoxyhemoglobin, whereas an increasing in pressure of oxygen or decreasing in proton shift the equilibrium to the left. The third effect is effect of 2,3-bis phosphoglycerate on oxygen affinity. In the beginning, 2,3-bis phosphoglycerate, or as we will called as 2,3-ppg, is an important regulator of the binding of oxygen to hemoglobin. The most abundant of organic phosphate in the red blood cell, its concentration is approximately that of hemoglobin, nearly similar to hemoglobin concentration. Also, 2,3-ppg is synthesized from the intermediate of glycolytic pathway. Now, in the beginning, binding of 2,3-ppg to deoxyhemoglobin. 2,3-ppg decreases the oxygen affinity of hemoglobin by binding to the deoxyhemoglobin, but not to deoxy. It is binding to deoxyhemoglobin, but not to oxyhemoglobin. This is as a result, as a conclusion. The effect of 2,3-ppg, it is decrease the affinity of oxygen, وبالتالي binding to deoxyhemoglobin, not to oxyhemoglobin. This preferential binding stabilize the T conformation of the deoxyhemoglobin according to the equation hemoglobin oxygen molecule plus 2,3-ppg, and it is in equilibrium of hemoglobin 2,3-ppg plus oxygen molecule. By increasing the concentration of 2,3-ppg, the reaction will be forward. So the complex of Hp2,3-ppg will produce. So hemoglobin oxygen will be dissociated. Binding site of 2,3-ppg. If we look for the figure here, this is hemoglobin structure. In hemoglobin structure here, we found that there is beta 1, beta 2, alpha 1 and alpha 2. Here there is a pocket between beta 1 and beta 2. 2,3-ppg, it will bind to the ionic positive, ionic in this pocket, and the binding here is stronger than the binding of hemoglobin with oxygen. One molecule of 2,3-ppg binds to a pocket formed by the two beta globin chain in the center of the deoxyhemoglobin tetramer. This pocket contains several positively charged amino acids that form ionic bond with the negatively charged phosphate group of 2,3-ppg. Shift of the oxygen dissociation curve. Hemoglobin from which 2,3-ppg has been removed has a high affinity for oxygen. However, as seen in the red blood cell, the presence of 2,3-ppg significantly reduces the affinity of hemoglobin to oxygen, shifting the oxygen dissociation curve to the right. This reduced affinity enables hemoglobin to release oxygen efficiently at the partial pressure found in that tissue. Then if the concentration of 2,3-ppg increase, and it is increased in the tissue. So in the tissue, the binding between hemoglobin and 2,3-ppg is stronger than the binding between hemoglobin and oxygen. So hemoglobin release oxygen and bind to 2,3-ppg.